Morning all, gravitational fields this morning. So these are the equations that you're given. Let's quickly go through what they mean. Little g here, this is the gravitational field strength, and what it is, it's force per unit mass. Okay, so remember gravitational fields, force per unit mass, just like electrical fields, it's force per unit charge. So this is the field strength, force per unit mass. Now you can rearrange this equation, F is equal to mg, and notice when we've got F equals mg, that's just F equals ma, isn't it? Whereas g, although we think of it as in newtons per kilogram, it could also be in meters per second squared. It's an acceleration. Now, you're also given this equation here. This is the force between two different masses. Now, it is Newton's law of gravitation. So Newton's law of gravitation, if you're stating it, is force is proportional to the product of the two masses and inversely proportional to the distance between the two masses squared. Okay, so this one is Newton's law of gravitation. Now, what we can do is if we have this equation and we have this equation, you can set them equal to each other. So you'd find minus gmm over r squared is equal to, well, mg. Now, if we do that, the masses cancel out, and you end up with this equation. G is equal to minus gm over r squared. Now this m here might be like the mass of the Earth. If we were wanting to work out the gravitational field strength about somewhere around the Earth, that would be the mass of the Earth. Okay, now this one, this is really Kepler's third law, that t squared is proportional to r cubed. They quite often get you to derive this. And if we're deriving this, we need our equation for force from Newton's law of gravitation. And you put that equal to, well, we're saying things are going round in circles. And you know that for centripetal force, force is equal to mv squared over r. Okay, so you can see that we can start looking at cancelling out some of the things. However, we want t in our equation, and we've got v squared. So we're also going to use the equation that v is equal to 2 pi r over t. Now, if we put this equation in for the v squared, it will be m times 4 pi squared r squared over rt squared. Then all you do is you multiply them all up. You see those m's cancel straight away, don't they? Multiply it all up and you'll end up with this equation. Have a practice at doing that because it does come up in around half of the exams. Okay, we went through these couple in the revision session, but just to remind you, you need to know your definition for the gravitational potential. So gravitational potential is the work done to move a unit mass from infinity. Now, if you want to know how gravitational potential varies with sort of distance away from the, or if we're doing it away from the Earth maybe, then what we'd do is we'd start, our first one would be sort of on the Earth's surface, and what would happen is it would get less and less and less until infinity it would get to zero. So you need to know that shape of the graph. This one here, the energy one, if we know the potential, then we can work out the potential energy. So the potential would be, if we were looking at the potential here, what would be the potential per unit mass of an object here to take it to infinity? The potential energy would be, if we had an actual object here and say we knew the object was 2 kilograms, how much to get the 2 kilograms to infinity. Now you can see all this one is really is that energy is equal to Vg, so the gravitational potential, multiplied by the mass of the object. So in this example, the 2 kilograms, okay? So those are those equations. Other things to make sure that you are aware of when you're doing the gravitational field, you need to know about Kepler's 3 laws. Now, I've already said that this one here, or just that the t squared is proportional to r cubed, that's Kepler's 3rd law. His 1st law is each planet moves in an ellipse around the sun with the sun at one focus. And the 2nd law is a line joining the sun to a planet will sweep out equal areas in equal times. So for the 2nd law, you might need to be able to draw an ellipse, a sun there, and then you're saying that, well, if the planet moved that distance in 24 hours, and then later on in the orbit, say it moved just that distance in 24 hours, the area of this sector would be equal to the area of that sector. Okay, I will be checking again later. Leave in the comments any other videos you want me to make today. Thank you.